Hello everyone, this is Swati from Aeronautical Engineering. The faculty name called Dr. D. Govardhan, and today we have an assignment of concept video, topic called Applications of Fourier's Law in Conduction. So, let's begin with the topic. First we have Introduction to Fourier's Law of Heat Conduction. Fourier's law of heat conduction describes the flow of heat in a material due to temperature gradient. It states that the rate of heat transfer through a material is proportional to the negative gradient of temperature and the material's thermal conductivity. Mathematically, it can be expressed as where is the heat flux K is the thermal conductivity and is the temperature gradient. This law is fundamental and foundationally in understanding heat transfer mechanism and is widely used across various engineering fields like aeronautical and every type of mechanical and chemical branches. So the second one is applications in heat transfer in solids. Fourier's law is primarily applied in solids to calculate the heat flux where there is a temperature gradient. For instance, in the digestion designs of heat exchangers, thermal conduction plays a crucial role in determining how efficiently heat is transferred between fluids and solid surfaces. The law helps engineers calculate the necessary materials and insulations required to maintain optimal temperatures and ensuring safety and energy efficiency. This is particularly important in applications like electronic devices where excessive heat generation could lead to malfunctions. Third one, thermal insulation in buildings. In the construction industry, Fourier's law helps in the designing buildings with effective thermal insulation. The heat flux through walls, windows and roof can be controlled by selecting materials with specific thermal conductivity. Using insulations, materials with low thermal conductivity such as fiberglass or foams reduces the rate of heat transfer, leading to improved energy efficiency. Fourier's law enables engineers to model and predict how heat will move through different materials, helping optimize designs for both heat and cooling system in residential and commercial buildings. Fourth one, heat conduction in metals. Metals are known to be good conductors of heat, and Fourier's law is crucially in describing the heat transfer process within them. In applications of cooking utensils, automotive engines, and electrical systems, metal efficiently transfer heat due to their high thermal conductivity. For example, in car engines, the engine blocks metal must efficiently conduct heat away from the combustion chamber to prevent overheating. Fourier's law is used to model heat dissipation rates and to choose the best metal alloy for specific thermal management applications. Fifth one, application in electronics and semiconductor industry. In electronics and semiconductor industries, managing heat is vital. Managing the performance and reliability of components, integrated circuits, ICs, transistors, and other electronic devices generates heat during operations, and Fourier's law is applied to calculate the rate of heat transfer from this component. The thermal conductivity of the material used in semiconductor fabrications determines how efficiently the heat is dispatched. Undertaking heat conductions help engineers design cooling systems such as heat sinks the fan, ensuring the safe operations of high performance electronics. Sixth one, heat conduction is geologically processes. Fourier's law is used to understand heat transfer in geological processes, particularly in the study of the Earth's interior. Heat conduction plays a significant role in determining the thermal gradient inside the Earth's crust. Scientists use Fourier's law to model how heat moves from the Earth's hot core towards the cooler surface. This is essential in understanding volcanic activity, the formation of minerals, and tectonic plates movements. By studying the heat flow in different layers of the Earth, geologists can gain insight into the planet's thermal history and further evaluations. Seventh one, heat conduction in fluids like convection and conductions. This is between the convections and conductions. In fluid systems, heat conduction plays a role in the thermal interaction between fluids and solids boundaries. Fourier's law is used to describe the heat conduction process when fluids are in contact with solid surface. For example, in heat exchanger, fluid is a different temperature exchanger heat through the solid walls separating them, while convection fluid motion is the dominant mechanism in most fluid based systems. Conduction through the solid materials is still essential in determining the overall heat transfer efficiency, and Fourier's law helps quantify these contributions. So the eighth one, the thermal management in spacecraft. Spacecraft are subject to extreme temperature variations. For instance, heat during sunlight exposure to extreme cold into showered regions. Fourier's law is applied in the design of spacecraft thermal protection systems. These systems use material with specific thermal conductivities to manage heat flux and prevent overheating or freezing of critical components. Engineers calculate the rate of heat transfer using Fourier's law to ensure the components such as engines, electronic devices, and life support systems remain within their operational temperature ranges, contributing to their spacecraft overall mission successes. Ninth one, biothermal heat transfer. In the medical and biomedical and biothermal with biological fields, Fourier's law is used to model heat transfer within biological tissues. The human body generates heat through metabolic processes, and understanding heat conditions helps in designing medical devices like thermometers, heating pads, and prostheses. For instance, during thermal therapy sessions, the rate of heat transfer through skin layers is crucial for determining heat treatments effectiveness and safety. Fourier's law is also important in studying hypothermia and hyperthermia, where the body's heat conduction properties affect how heat is distributed or lost. 10th one, cryogenic and low temperature application. In cryogenics, where temperatures are extremely low, heat conduction is critically aspect of system design. Fourier's law is used to predict the behavior of material when exposed to cryogenic temperatures, such as in the storage of transportation of liquefied gas like nitrogen and helium. Materials must be carefully selected of their low temperature and low thermal conductivity at these temperatures to prevent heat ingresses which could cause the liquefied gas to evaporate. Additionally, understanding heat conduction helps improve insulations in techniques in cryogenic tanks and systems. 11th one, micro and nanoscale heat transfer. At micro and nanoscale level, Fourier's law still holds, but this mechanism of heat conduction can differ from those observed at microscopic scale. As materials becomes smaller, phenomenon interactions, quantum vibrations within materials dominate heat transfer, and Fourier's law is applied with modification to account for the unique properties of nanomaterials in microelectronics. For example, the heat generated by devices like microphones, like micropropellers, requires precise control to avoid overheating, and the law is used to calculate heat fluxes in these tiny systems, aiding in the development of effective cooling strategies. 12th one, heat conduction in polymer materials. In polymer science, Fourier's law is employed to study of the heat conduction properties of polymers using a packaging insulations. The medical devices polymers typically have low thermal conductivity, making them ideal for insulation application. However, in this process, like injections modeling or 3D printing, controlling heat transfer is critical to achieving the desired properties of the final product. Engineers apply Fourier's law to optimize manufacturing conditions, ensuring that the thermal response of polymer materials is consistent throughout the processes. So 13th one, energy harvesting from temperature gradient. Fourier's law is central to the field of thermoelectrics, where heat gradients are used to generate electricity. By applying the law of calculate heat transfer occurs thermoelectric materials, engineers can design devices that harvest energy from the waste heat. This principle is applied in technologies that convert temperature difference into electrical power, such as in spacecraft, automotive systems, and variable electronics. Fourier's law helps optimize the materials and configurations to maximize energy conversion efficiency, making thermoelectrics promoting technology for renewable energy generations. So 14th one, environmental and climate modeling. Fourier's law is applied in climate science and environmental modeling to understand heat flow within the Earth's atmosphere, oceans, and surfaces. Scientists use it to model how heat moves through various layers of Earth's environment, influencing weather patterns, climate change, and heat island effects in urban areas. Understanding the rate of heat conduction in the soil, water bodies, and atmosphere allows for better predictions to temperature fluctuations and helps inform climate policies as well as strategies for mitigating the effective effects of global warming. 15th one, heat conduction in nuclear reactors. In nuclear reactors, Fourier's law is essential for understanding and managing the heat generated by nuclear fusions. The fuel rod within reactors undergoes fusion reaction, realizing large amount of heat that must be conducted away to prevent overheating. Fourier's law is used to model the heat transfer from the fuel to the coolant and to ensure that the materials used in reactors construction can efficiently conduct heat while maintaining structural integrity. Proper heat management is vital for reactor safety and efficiency. So now 16th one, thermal stress and strain in materials. When heat flows through materials, it causes thermal expansion, which can induce stress. Fourier's law is used to predict temperature distribution and the resulting mechanical stress within materials subjected to thermal gradient. This is particularly relevant in aerospace engineering, where components like turbines, blades, jet engines, and spacecraft undergo extreme temperature changes. By applying Fourier's law to thermal conduction models, engineers can predict potential failures points and design materials that can withstand thermal stress without cracking or deforming. Moving to 17th one, heat conduction in cooking application. Fourier's law finds practical application in cooking, where heat conduction is the primary mode of heat transfer from cooking surface to food. The rate at which heat transfers through a pan to the food depends on the thermal conductivity of the pan material and the temperature gradient. For example, materials like aluminum and copper with high thermal conductivity are used in cookaways to ensure even heat distribution. Fourier's law allow cooking and manufacturers to optimize cookware designs for energy efficient cooking and consist results. 18th one, conduction in nanostructured materials. In the real name of nanotechnology, Fourier's law is used to understand the heat conduction behavior in nanostructural materials such as nanowires, nanotubes, and thin films at the nanoscale. Heat conduction is influenced by factors like scratching and quantum effects, which differs from the traditional microscopic behavior. Researchers apply modified forms of Fourier's law to investigate how heat moves through these materials, adding in the development of novel applications such as thermal efficient coating, nanoscale thermal scissors, and advanced cooling systems of electronic devices. Moving to 19th one, heat conduction in chemical energy. In chemical energy, Fourier's law is applied to study heat transfer during processes such as distillation, chemical reactions, and materials processing. The law helps engineers design equipment like heat exchanger reactors and evaporators that rely on efficient heat transfer. By using Fourier's law, engineers can calculate the necessary temperature gradients to achieve desired reactions uh, rates and optimize energy consumptions in chemical manufacturing. This is particularly important for industries where maintaining precise thermal conditions is crucial for product quality and process efficiency. 20th one, conclusion, and the last one, conclusion and the further trends. Fourier's law of heat conduction is fundamental principle with widespread applications in various fields of science and engineering. As technology advances, particularly in nanotechnology, materials science, and renewable energy, the law continues to evolve with new models to describe heat conduction at small scales to or understand extreme conditions. Its applications in electronics, conduction, space exploration, and environmental science will remain vital, and as society continues to seek more efficient way to manage energy and heat transfer in both industrial everyday content. So thank you.